Parker's solar probe skimmed the edge of an interstellar comet's tail. The readouts weren't normal. This wasn't a glitch. Parker's instruments lit up with signals that didn't match anything in the database. Magnetic fields twisted in ways solar wind shouldn't twist. Particle detectors picked up ions with ratios we've never seen in our solar system. The comet is called 3I Atlas, the third confirmed visitor from beyond our sun. It came from somewhere else, another star, another planetary nursery billions of years old. And for a few hours, humanity's fastest spacecraft flew through its wake. If the signals line up, this could be our first close taste of matter from another star's nursery. Not through a telescope, not from light years away, direct sampling, instruments touching the debris of a solar system we will never visit. Parker wasn't built for this. It was built to study our sun. But on that October day it became something else, an accidental probe into interstellar space. What did Parker's instruments actually pick up? That's the question keeping mission scientists up at night. Because if those readings are real, everything changes. The composition, the magnetic fingerprint, the chemistry locked inside those particles. We're about to break down what happened in that tail and why it might rewrite what we thought comets could be. Interstellar comets carry ions shaped by their birth clouds. That's not speculation, that's physics. When a comet forms, it locks in particles from the nebula around its parent star. Those particles carry a signature, a magnetic orientation, a chemical fingerprint. Even after traveling for millions of years through deep space, those patterns survive. Think of a leaf drifting on a river. The river is the solar wind. The leaf still carries old pollen from the tree it fell from. Same concept. The comet's tail gets pushed by our sun's wind, but the particles inside remember where they came from. Parker's Fields instrument measures magnetic fields at millions of samples per second. It's built to track how the sun's magnetism behaves. But when it crossed 3I Atlas's tail, scientists weren't just looking for solar wind patterns. They were hunting for something older, a twist, a misalignment, a magnetic field orientation that doesn't match the local environment at all. If Fields caught that, it would mean one thing: memory. A magnetic fossil from another star's cradle, locked inside the tail of a visitor we will never see again. That idea should thrill you. It means Parker touched a story older than our sun, older than Earth, a fragment of a system that built its own planets in its own way. And we might have the data to prove it. SWEEP can taste ions in the wind. It can tell heavy from light, carbon from oxygen, water molecules from carbon monoxide. That's what the solar wind electrons, alphas, and protons instrument does. It samples everything flowing past the spacecraft. In normal conditions, it reads the sun's output: hydrogen, helium, standard solar particles. But in a comet's tail, the mix changes. Some researchers watch for unusual ratios: carbon to oxygen, nitrogen to carbon, deuterium to hydrogen. That kind of clue matters, because every solar system forms from a collapsing cloud of gas and dust. The temperature, pressure, and chemistry of that cloud shape what survives. Our system formed at a specific distance from the galactic center, specific conditions, specific materials. A comet from another system formed somewhere else. Different star, different disk, different rules. A strange pattern in Parker's ion readings would hint at a protoplanetary disk unlike ours. Not wildly alien, just different enough to notice, like tasting water from a foreign river and realizing the minerals don't match home. What ratio would convince you this came from a different kind of system? If Parker sees out-of-family ion patterns, we get a direct sample of another system's building blocks. Not light from a distant star, not a spectrum filtered through space, direct particles, raw material. That raises a big question. How many ways can solar systems form? Are there templates, or does every star birth planets differently? One ion ratio won't answer that, but it's the first brick in a foundation we've never been able to build before. The next clue isn't chemistry, it's motion at dust grain scale, and it matters for starflight, because what happened when Parker hit those grains at 700,000 km/h could teach us how to survive the journey between stars. Parker is fast and faster than any object we've flown. At peak velocity, it hits 700,000 km/h. That's not a casual number. That's a spacecraft moving so quickly that time itself shifts slightly compared to Earth. When you're moving that fast, dust isn't just dust anymore. A grain the size of a sand particle becomes a bullet. A speck smaller than a human hair becomes a micrometeorite, traveling at tens of kilometers per second, relative to the spacecraft. When those grains hit, they don't bounce off. They vaporize instantly. The impact creates a tiny explosion of plasma. Electrons and ions burst outward in a flash. Parker's Fields instrument can sense the electric pop, a spike in the data, a brief disturbance in the electromagnetic field around the hull. The spacecraft logs it, records the signature, moves on. But that blip is data, real data on how craft survive deep space at interstellar speeds. This helps design shields for future interstellar probes, missions like Breakthrough Starshot, concepts for laser-pushed light sails aimed at Alpha Centauri decades from now. Those missions will hit dust clouds at a fraction of light speed. Engineers need to know what happens, how plasma forms, how hulls respond, whether electronics survive the cascade. Parker just gave them a test case. Not at light speed, but fast enough to matter. This is not just a comet story. It's a blueprint for the ships we haven't built yet. In a small flash of plasma, you can glimpse the future of star travel. The violence of it, the engineering required, the reality that space between stars is not empty. It's filled with debris. And if we're going to cross it, we need to learn how interstellar debris meets the sun's outflow. It is a push and a bend. The solar wind doesn't stop at Mars. It extends outward in a bubble called the heliosphere. That bubble protects us from galactic cosmic rays, high-energy particles streaming through the Milky Way. When something from outside enters that bubble, it interacts. The wind pushes against it, shapes it, sometimes deflects it. If Parker saw the wind bend more than expected during the tail crossing, that tests our shield, the heliosphere itself. How strong is it really? How well does it repel foreign material? Does interstellar dust penetrate easier than we thought? These aren't abstract questions. They matter for radiation exposure, for spacecraft electronics, for human missions beyond the moon. The next part sounds technical. It isn't. It's a weather report for the space around us. And the forecast just got a visitor from out of town. The sun blows a bubble. We live inside it. That bubble is the heliosphere, a region where the sun's magnetic field and particle wind dominate. It stretches past Pluto, past the Voyager probes, out to where the pressure of interstellar space finally pushes back. Inside that bubble, conditions are relatively stable. The solar wind flows outward. Magnetic field lines spiral. Charged particles follow predictable paths. An interstellar tail is a draft of different air meeting our wind. 3I Atlas brought particles shaped by another environment. Different magnetic orientation, different chemistry, different pressure history. When that tail entered the heliosphere and approached the sun, it met resistance. The solar wind tried to push it back, compress it, reshape it. If the tail slowed or turned the wind, Parker would see it. Fields would register a shift. Sweep would detect unusual turbulence. The magnetic field lines wouldn't look normal. That kind of disturbance matters for radiation risks, for astronauts, for satellites, for the next crew leaving Earth orbit. The heliosphere shields us from cosmic rays. But if interstellar material can disrupt the wind, it means our shield isn't a solid wall. It's more like a screen, permeable. A visitor's breath changed our local breeze. That should give you chills because it means the boundary between our system and the galaxy isn't as sharp as we thought. It means we're constantly exchanging material with deep space. And if that exchange accelerates, the radiation environment around Earth changes, not catastrophically but measurably. That's the kind of data Parker wasn't designed to collect, but it might have. Anyway, isotopes are the same element with different weight. Take hydrogen, the lightest element. Normally it's one proton, one electron, simple. But sometimes hydrogen carries an extra neutron. We call that deuterium, heavy hydrogen. When you measure water, you can count the ratio deuterium to hydrogen, DH. That ratio tells a story. It reveals temperature, pressure, the conditions when that water formed. Earth's oceans have a specific DH ratio. Comets from our solar system cluster around a range, sometimes higher, sometimes lower, but within a family. An interstellar comet might not fit that family. Parker's particle sensors can't run a lab. They can't freeze samples and weigh atoms precisely, but they can hint at unusual heavy-to-light ratios. If SWEEP or ISIS detected ions with masses that don't match the expected distribution, scientists would flag it. Compare it to known comets. Check if it falls outside the pattern. A different ratio would mean water from a different recipe, a different sun story. It would mean 3I Atlas formed in a colder region or a hotter one, or near a star with different metallicity, different building blocks entirely.